is, in 6.4, we're going to talk about integration using partial fraction decomposition. So we're going to spend some time reviewing partial fraction decomposition so that we can use it. But what I want you to see is, or I want you to remember, is that I'm taking something like 5 over x squared plus 4x plus 3, and I'm breaking that up into a over x plus 3 plus b over x plus 1. And before I even remind you how to do a problem like this, I want to show you why doing this can help you with integration. Noticing that the numerator is 5 in the original expression, if we integrated, we can temporarily just assume that a and b are some constants. If I have something like this, I can split that up into two integrals, over x plus 1 dx. And then I'm just going to get a natural log absolute value of x plus 3 plus b natural log absolute value of x plus 1 plus c. So by being able to take something like this, which we may be able to manipulate in a different way, but nothing really stands out immediately there, this would enable us to simplify this problem using a tool from pre-calculus, which is always nice when we can go back and use something that we already know how to do to simplify a problem. So let's review how to actually do partial fraction decomposition. So in order to find our a and b values, the way that you probably learned this before is that we're going to multiply b over by x plus 3 over x plus 3. And we're going to multiply a, which I don't have the room for, by x plus 1 over x plus 1. And that gives us that ax plus a plus bx plus 3b equals the original numerator, which is 5. From here, we can set up a system. We can include all of our x's together. Ax plus bx is going to equal 0, since there is no x term in the numerator. And we can include all of our constant terms. A plus 3b is going to equal 5, which is the number in the numerator. We could then drop the x's in the first equation and multiply everything by -1, or however you want to solve the system. -a minus b equals 0. That's going to give you that 2b equals 5, which means that b is 5 over 2. If b is 5 over 2 and a plus b is 0, that means that a is -5 over 2. Which means that we could rewrite this whole expression instead of having, I'm going to just go back and edit this so I have a little bit more space. We could rewrite this whole expression as either with 5 over 2 in the numerator for both a and b, or with 5 over 2 in front. Since we're likely going to use this to integrate, I would recommend putting 5 over 2 in the front, 5, since it is the same for both a and b. And then I would change this to be a minus sign. But you could write 5 over 2 over x plus 3 plus 5 over 2, -5 over 2 over x plus 1, either way. So the goal here really was taking a trinomial denominator and turning it into two binomials, or decomposing it into linear factors, which will help us integrate, as we just mentioned. So there's actually a faster, more efficient way to decompose fractions than setting up this system, and you're more than welcome to use this system, but it just takes a little bit of extra time. And this method is called the Heaviside method. So I'm going to show you how to decompose fractions using the Heaviside method. It's your choice how you decompose fractions, but it is a skill that you should be able to do in order to help us simplify an integration problem. So I'm going to go ahead and delete all of this on the top. All right, so now we have some more space in order for me to show you the Heaviside method, also known as the cover-up method. So how this method works is, I'm going to try and color coordinate here. In order to find a, you're going to identify what would make the fraction that has the a factor underneath it undefined, or what would make the denominator 0. So that is going to be when x is equal to 0. Then you're going to take that x value, you're going to cover up that factor and plug 0 in for x and what's remaining, and that will give you your a value. So a is going to equal 4 over 0, because that's what would make the denominator under a be undefined, plus 4. So a is going to equal 1. Now we're going to follow the exact same process with b. All right, to find b, let me erase this purple. To find b, which I'm going to do with blue here, you're going to cover up the factor under b in your original 4 over, your original factored expression, 4 over x times the quantity x minus 4. And you're going to plug in for x the value of x that would make the fraction under b undefined. So when x is equal to -4, this would be b over 0, which we can't have. So you're going to plug -4 into the other factor. So b is going to be equal to 4 over -4, which is -1. Then we can take our a value and rewrite this as 4 over x squared plus 4x is equal to 1 over x plus -1 over x, or you could change this to be a negative sign here. Either way, that's going to give you your factored expression. In class, we're going to talk about why the Heaviside method works. We're not going to focus on that in this video. It would make this video too long, so I will go over that in class. There's also an explanation of the Heaviside method with more examples in Google Classroom. Remember, you do not have to do it this way, but look at the amount of work that I showed to find a and b. It is significantly less than creating and setting up a system and solving that system. It will take less time. This is the method I'm going to be doing when I'm solving. You do not have to show any more work, even though I kind of wrote out an explanation how I found A and found B. You do not have to do that. College Board understands that you may be using the Heaviside method in order to find your A and B and potentially C values. So I want you to notice number 1 is the integration of this partial fraction that we just found here. So I'm going to move on to the next slide so that we have more space to do this problem, but I'm going to start with having already identified what A and B are here. So since we already did that partial fraction decomposition, we can rewrite this as the integral of 1 over x minus 1 over x plus 4 dx. And then we can just integrate. This is going to give us natural log of the absolute value of x minus natural log of the absolute value of x plus 4 plus c. So much easier than trying to find a different way to manipulate this problem. So partial fraction decomposition is one that's going to come into play a lot of times when you see something in the numerator and the denominator having to deal with polynomials. And we're going to focus in the second part of this lesson of figuring out, should we be using partial fractions or some other strategy? We're going to talk through that in this lesson as well. So I want you to go ahead and pause the video, and whether you're going to use substitution or the Heaviside method, I want you to rewrite this expression, 7x over x squared minus 3x minus 10. I want you to rewrite that using partial fractions. So to find a, we're going to use x equals 5. You're going to plug 5 in and cover up the x minus 5 term. That's going to give you 7 times 5 over 5 plus 2, which is going to give you 5 as your a value. Unless you set this up, I set this up as a over x minus 5, a over x minus 5 plus b over x plus 2. If you set this up in reverse, obviously your a and b values are going to be switched. To find b, I'm going to substitute in x equals -2, and I'm going to cover up that factor. So 7 times -2 over -2 minus 5 is going to give us +2. So now I can rewrite this problem using my a and b value. So here is my rewritten integral. Oops, sorry, that 5 looks a bit like a 15 right now for no reason. And now I can integrate. And when I integrate, I'm going to get 5 natural log of the absolute value of x minus 5 plus 2 natural log of the absolute value of x plus 2 plus c. So why don't you go ahead and pause the video and work through number 3. Then unpause the video to see how you did. and then work through number 4. Number 4 is going to take a little bit more work, but you can still use the Heaviside method. You're just going to have to find an A, a B, and a C value. So go ahead and pause the video and work on those 2 problems. So on number 3, I set mine up where A was over 2x minus 1 and B was over x plus 1. So A ends up being 3, B ends up being negative 2. You can pause the video and kind of check my math there. So then I can rewrite this integral. And to integrate my purple portion, 3 over 2x minus 1, I need a 2 in the numerator, and which means I need to multiply by 2 and multiply by 1/2. So that's going to give me 3 times 1/2, so 3 halves, times the natural log of the absolute value of 2x minus 1, minus 2 natural log of the absolute value of x plus 1 plus c. All right, and on to number 4. So on number 4, the bottom factors to be 3 different factors. So we're going to have a over x plus b over x plus 2 plus c over x minus 2. Now go ahead and use the Heaviside method to find a, b, and c. So once you find a, b, and c, which I have done in this bottom corner section, you're going to get the integral of negative 3 over x plus 1 over x plus 2 plus 5 over x minus 2. And we're going to have a whole bunch of natural logs happening here. This is going to be negative 3 natural log of the absolute value of x plus the natural log of the absolute value of x plus 2 plus 5 natural log absolute value of x minus 2 plus c. So there's our final answer. I apologize, this is so sloppy. All right, now what we're going to do is really focus on recapping the methods that we have learned, looking at some common options when we see polynomials, some common methods that we may use, and really dissecting how do I approach a problem beginning to end involving integration. So we have talked about a handful of strategies that can be applied when we have a rational expression, a polynomial over a polynomial, or something like these 3 examples that are shown below. And I kind of want to summarize an appropriate strategy or how to approach when we have a situation like this. So when the denominator does not nicely factor, that's a great indicator that you should complete the square. So for example, on this problem over here, I'm going to call it the purple problem. On this purple problem, the denominator doesn't factor. If it was x minus 8, it would factor, and we could use partial fractions here. But x squared plus 4x plus 8 does not factor. So what we can do is we could rewrite this as 3 times the integral of 1 over, and we can complete the square in the denominator. This is going to become x plus 2 quantity squared plus 4 dx. In the denominator, I notice that I have the sum of 2 squares. In the numerator, I have a constant. So this is an arctan situation where a is equal to 2. So this is going to become 3 over 2 times arctan of x plus 2 over 2 plus c. Now, one of the things I have repeatedly reminded you is don't forget the things that you have always known to be true since the very beginning of integration. U-substitution is still often a viable option. So always at least mentally check, could I use U-substitution? So on this second one, if I let u equal everything in the denominator, that would give me that du is 2x minus 7. And that happens to also just be what was in the numerator, dx. So that means that this is going to become the integral of 1 over u du, which is just natural log of the absolute value of u plus c, or natural log of the absolute value of x squared minus 7x plus 5 plus c. So don't forget that U-substitution is often a viable option. We get into the habits of just trying these more difficult strategies when that's not always necessarily the case. And then remember that it's always possible, if your degree of your numerator is greater than or equal to the degree of your denominator, it's always possible that you might actually want to divide first. So I'm going to go ahead and do long division here and then rewrite this fraction. So there I have rewritten it using long division. I can just integrate x to get x squared over 2, and then I'm going to split the fraction for my other two. So this is 1 over x squared plus 4 minus 4x over x squared plus 4 dx. This first part is going to end up being arctan, and we can use U-substitution on the second part to actually get a natural log situation. So let's work through that. So I'm going to take this piece that I'm kind of surrounding with black, and I'm going to work on it down here. So I'm out of space a little bit. I'm going to let u equal x squared plus 4, so du equals 2x dx. So that integral is going to become the integral of negative 4x over u times du over 2x. So this 2x is going to divide out with this negative 4. So I'm going to have negative 2 natural log of u, which was x squared plus 4 plus c. So those are 3 other strategies. We talked about partial fractions. That's strategy number 4, completing the square, dividing first, using U-substitution. Keep all of those strategies in mind when you are approaching a problem that has a rational expression. Now let's look at 4 more examples and practice identifying an appropriate strategy to work through each one, and then actually using that strategy to integrate. All right, number 5. So my first thing that I notice is that the degree of the numerator is greater than the degree of the denominator, so I'm going to go ahead and divide first. That's going to get me here. This first term is just going to become x squared over 2. This second term is going to become plus the integral of 1 over, and I'm going to split this up since regular U-substitution isn't going to work for me here. I'm going to split this up, and then I'm going to end up using partial fractions, I believe, on this blue portion. And then this purple integral, 4x over x squared minus 4, I think we can just use regular U-substitution there to simplify that portion. So I'm going to come down here and find a and b. I'm going to do the partial fraction work down here. Equals 1 over x plus 2 times x minus 2. So a is going to be negative 1/4, b is going to be positive 1/4. So I'm actually just going to factor 1/4 out of that entire integral and rewrite that. Now I'm going to come back and deal with that purple, but right now I can go ahead and actually complete this integration. That's going to be minus 1/4 natural log of the absolute value of x plus 2 plus 1/4 times natural log of the absolute value of x minus 2. Now I'm going to deal with this purple portion. So I'm going to let u equal x squared minus 4, so du equals 2x dx. So this is going to become the integral of 4x over u times du over 2x. So this is going to become what? 2 over u du, so plus 2 natural log of u, which was x squared minus 4 plus c. So go ahead and pause the video if you need to look over that. I'm going to erase this partial fraction work that's covering number 7 so that we can keep going. Number 6, I again see that the degree of the numerator is equal to instead of greater than, but still I can do some long division here, and I think that's going to simplify my problem, so I'm going to do that first. So after I perform that long division, I'm going to get the integral of 1 plus the quantity x plus 1 over x squared minus x, or x times x minus 1. So trying to figure out how to deal with that integration now. Obviously 1 is just going to integrate to be x, but dealing with that second term, I again think we're going to need to do some partial fraction work. So I'm going to do that down in number 8. I'm looking for a over x plus b over x minus 1 equals x plus 1 over x times x minus 1. I'm going to find a, which is going to happen when x is equal to 0. So find a. If x is equal to 0, I get 1 over 0 minus 1, so I get negative 1. If I'm going to find b, that's going to happen when x is equal to 1. That's going to give me 1 plus 1, or 2 over 1. So b is going to be 2. So I can rewrite this, and I'm just going to integrate that first part to get x plus the integral of negative 1 over x plus 2 over x minus 1 dx. So that's going to give me x minus natural log of the absolute value of x plus 2 natural log of the absolute value of x minus 1 plus c. Why don't you go ahead and pause the video and work through 7 and 8 on your own, and then unpause the video and see how you did. So on number 7, I'm going to do long division first. So the integral of 1 is just going to become x. I know that I'm eventually going to evaluate that from 0 to 1, but I'm just going to leave it as x for right now. Actually, let's write that so that I don't forget. Minus the integral of 2x plus 1 over, and actually, looking at this, if I let u equal x squared plus x plus 1, du would be 2x plus 1, and that's exactly what I need it to be, 2x plus 1 dx. So over u times du over 2x plus 1. So those 2x plus 1s are going to divide out. Don't forget about U-substitution. It is your friend. So this is going to be, actually, I don't want to do that with my bounds. I need to change my bounds. If u is x squared plus x minus 1, if u is 0, I'm going from 1. If u is 1, I'm at 3. So I'm going to evaluate x from 0 to 1 minus natural log of the absolute value of u from 1 to 3. Well, x from 0 to 1, I guess I could have done this a while ago. When x is 1, I have 1. When x is 0, I have 0. So that is just going to become 1 minus natural log of 3 minus natural log of 1. Well, natural log of 1 is just 0. So this is going to become 1 minus natural log of 3. All right, go ahead and pause the video and try and work through number 8. Notice on number 8 that the denominator does not factor. So I'm going to factor a 3 out, and I'm going to complete the square on the bottom. This is going to become x minus 3 quantity squared, 9 and 16 plus 7. And this is going to give me arctan, where a is the square root of 7, so 3 over 7 times arctan of x minus 3 over the square root of 7 plus c. So the key thing that this section really covered was, how do we approach rational expressions with integration? Does it factor? Could I complete the square? Could I just use regular old U-substitution? Could I divide first? Do I need to use partial fractions? So really make sure that you're thinking through each of those strategies every time you see a polynomial expression for a problem like this with integration. Looking forward to supporting you on this in class. Thanks for listening.